Assalamu alaikum. This is the first video for this subject, and I hope all of you are doing great. And if you remember, so far we have covered the first part for this subject, which was different hazards, and the second part of this subject, that was disaster management. So from this video onwards, we will be starting this topic of disaster management, starting with the first hazard that we had covered, which was earthquake. And then the other hazards, floods, and the other ones will follow. So just a quick reminder that we have already covered in all the 4 sections before the midterm exam. I had covered all the hazards as far as I remember up to the heat wave topic. So if in any section somehow any of these topics that was skipped or missed, then the notes I have already posted in the Google Classroom, so you can go through those handouts, and if there are any questions you can ask. So starting with this topic of earthquake disaster management, we if you remember have to basically follow these 4 steps, starting from the mitigation stage, then preparedness, response, and recovery. So one important point here is that this is a multidisciplinary field, this disaster management, and it can have several dimensions, but we mainly have to discuss it from civil engineers point of view. So all the points that I have listed here, you will see that they include mostly those topics which are related to civil engineers. You won't find or in detail, I have listed them here, but we will not be discussing them in detail, that how to provide first aid to the injured or how to do the search and rescue operations. So our main focus will be on the structural measures which we can take to minimize the damage from any expected earthquake event, or if the event has already happened, then how we can minimize its impact. So the first one that you can see here, that is strengthening and retrofitting under the mitigation stage, then seismic proofing. So we will see in this video, basically we have to cover this mitigation part only. So we will see this in detail, that what retrofitting is, how it is done, then seismic proofing, different approaches for making buildings seismic proof, and then the other ones, these 3 stages we will cover in the next video, which is the early warning system, the safety kit, and the evacuation plans or evacuation drills. And again, in response, we have the evacuation, first aid, search and rescue, and in recovery, similar to mitigation, we have reconstruction stage and the retrofitting and repair stage. Starting with this mitigation part, we have 2 main approaches being a civil engineer. One is strengthening or retrofitting. The second one is seismic proofing. So the first part, the strengthening or retrofitting, I will be discussing it after covering the second one, which is seismic proofing. I have a separate presentation file for it, so I will try to cover it in detail, that how earthquake damaged or earthquake vulnerable structures, they can be improved for an expected or for the next expected earthquake. So starting this slide with the seismic proofing, there are several approaches which can be adopted to make a building seismic proof. Not exactly or not 100% seismic proof, but we try to minimize the impact of ground motion which is expected from an earthquake. So in seismic proofing, we try to minimize the impact, or we try to increase the capacity of a structure against an expected earthquake. So some examples I have listed here, that some of the very famous ones, the base isolation or the base dampers, the tuned mass dampers. Then another approach can be that we can change or improve the structural systems, that we can provide shear walls, we can provide braced frames. So just for the time being, keep these 3 or 4 terms in your mind. One is base isolation, second one is tuned mass dampers, then these structural systems, the shear wall and braced frames. For the time being, keep these terms in mind. In the next 10 to 15 minutes, I'm going to cover them in detail, And then if there will be any question that you can post as comments under this video, or you can directly send me an email and we can discuss them. So starting with even before this base isolation or tuned mass dampers, the first thing is the research in this field, in the field of seismic proofing or constructing earthquake proof or earthquake resilient structures is, excuse me, one, for the time being, please just watch this video. Okay, so here what you are looking at is a full-scale multi-story building which is being subjected to an artificially induced ground motion. This is the largest shaking table in the world, which is in Japan, and it is called E-Defense. E is for earthquake and defense, this is its name. This is the largest possible shaking table that we have currently in the world, and it is in Japan. And I was fortunate enough to work on this shaking table, and I will be sharing some more pictures of this shaking table with you after we cover this video. So what is going on here is that they are trying to test several new things. One is this material. The whole building is composed of mainly the material, building material is wood in this case, and then different types of connection devices, which Simpson Strong Tie you can see here, that is the company which manufactures them. So the idea is, or the idea of showing this video is that this sort of research, experimental or on the basis of these experimental results, the analytical or the software based result, that is very important to make sure that any new structural system or any new plan or any new material that we are trying to use for future structures, that is proven to be safe. So we try to ensure with such full scale or the scaled down model experiments, we try to ensure the safety of these structures when they will be exposed to real earthquakes. So here a real earthquake which had hit Japan in the past, that is being applied or that is being simulated on this actual model of a building, which is full scale model. In this E-Defense, what happens is that this is its main entrance gate. On the other side of this gate, there is one open area where they assemble this structure. Then with the help of these cranes, you can see 50-ton crane is, it is having capacity of 50 ton. There are several such cranes available here. So they lift this building, they put it on top of this shaking table, and then the building is at any desired earthquake level or intensity. The building can be tested, or any other model or any other structure that can be tested. I will give some other examples of structures. So here, if you look at this video, the next will be the interior view of one of the rooms. Before that, these are the sponsors for this experiment. This is by far, this is the largest shaking table experiment that has been conducted in the world. We also have one shaking table in our earthquake lab in our department. If you happen to visit, if you have visited earthquake lab of our department, you can find one significantly smaller than this one, but that is a very common scale that you will often find in most of the universities. They have that sized shaking table for research purpose, not for industrial application. So this is one room inside the building that you have just seen, and when the earthquake was applied, this is the condition of the inside of that room. And based on these observations, obviously a lot of data from these cameras that you can see which are installed here, several sensors are installed, overall the condition of foundation, and then the main structural components, and then the non-structural components. For all of them, the response, it was recorded, and then accordingly further improvements they were made. Some more pictures from this e-defense setup, like you can see here. This building as well as this next building, these are not buildings as such, these are actually test samples or test specimen which were tested on that same shaking table. Behind this building you can see that building is it which in which that e-defense is located. So this one is a hospital building, a three-story hospital building, which was tested for assessing its seismic performance. And this is one school building, which was again tested. You can see that the columns are damaged. So these there were several other specimens which were dismantled and they were recycled. These were also supposed to be dismantled and recycled. So if you happen to visit this facility in future, you may not find these buildings present there. Then, just to give you an idea about the scale of this setup, this is a pumping station for this e-defense, means which pushes or which gives energy to that shaking table. This is a separate setup. And overall, the size of this one or the area that is more than the area of our whole department or significantly more than that. So that is just to push that shaking table. So then coming back to the presentation, or the three approaches which we are supposed to see. The first one is base isolation or dampers. So the idea behind these three approaches is that the procedure that I have already mentioned to you, which is the experimental testing of different approaches. Like one example you have seen, a testing of a wooden multi-story building. Similarly, these different devices, the base isolation devices, the tuned mass dampers, or these structural systems, they can be experimentally evaluated or numerically using some experimentally verified software. These devices, they can be evaluated, and then based on their performance, their design can be optimized. So now we will discuss them one by one. First of all, it is base isolation. So for base isolation, one of the examples or one of the most common types of isolation device that is used is this sort of damper. So this is one multi-story RCC structure. This is its, you can say, the start of the superstructure, and this is its substructure. And in between, there is this separation that is provided. This is a damper. A damper is basically a rubber or rubberized material which is having several metallic sheets or plates which are sandwiched between this rubber. You can find several dampers which are used for bridges in our test floor lab. They come there for testing, but this one is a dynamic damper, and its purpose is to dissipate the energy or to reduce the ground motion which will be shifted from this ground to the superstructure. About 30 to 40, depending on the design, a significant portion of that ground motion can be dissipated at this level. So this is a small gap that is left between the substructure and superstructure, which contains these dampers. And another benefit is that it contains these supply or utility lines, that this sewerage system, water supply system, all these supply lines, they are also accommodated within this gap. So most of the pictures that I'm showing you, including these ones, they were taken by me, and these were present in Japan. And the idea of telling this is that these are not the theoretical objects. These are very much in use for the last couple of decades, that most of the buildings, like the ones I showed you in our earthquake hazard part in Japan, the buildings which were performing really well, they were actually, they were seismically resisted, or their performance was improved by the incorporation of such kind of devices. Then this is the same kind of damper. You can get an idea that this is the substructure, and then this is column. These are beams for the superstructure, and a set of such dampers is placed, and whenever there will be shaking, a significant portion of that will be dissipated here, and only a few portion will be, or a smaller portion will be shifted upwards. Then another kind of energy dissipation device, which is just besides this one, in the same building, that is this horizontal energy dissipator. So the idea is, this is again supporting one column or a part of the superstructure. The idea is that whenever there will be excessive lateral deformation or a significant ground motion, these devices, they will break from either here or here, and a significant portion of energy will be dissipated for their breakage or for their failure, and a lesser amount of energy then it will be transferred to the superstructure. Means we are defining predefined failure locations, that here the maximum failure will take place in the superstructure, or any failure to superstructure that can be avoided. And later on, when the earthquake is over, we can jack them or the superstructure part up, and we can replace this device with a new one for any future expected earthquake. Then similarly, that was for the previous one, that was for horizontal shaking. This one is mainly for vertical shaking. You can see these four fork or U-shaped steel rods. They are supporting a part of the superstructure, and in case of vertical excitation or vertical movement of ground, this will be resisting that, or this will be dissipating it. This will try to avoid the direct transfer of vertical motion from this point to this point, and this will be damaged to some extent, which can be later on repaired or replaced. Then this is another energy dissipation device in the same building. A part of the column is intentionally kept weak, and some margin of expansion is also provided. But in case of a strong ground motion, a part of it that is dissipated here, and if it becomes more than the capacity of this column, instead of the failure of this whole column, only a part of it or this specific part, it starts yielding, and maximum energy is dissipated here. And this part, it can be later on replaced with a new component, a new similar component. So these are different energy dissipation devices which are very much in use these days, and there can be several other types. These are only a few which are present in this building that we visited, but in most of the seismically you can say well designed structures, these components are very common. Then coming back to this part, this next is tuned mass dampers. The previous ones, those were base isolators that we try to isolate the substructure from superstructure, and whenever there is strong motion of the substructure, the superstructure will be observing a significantly lesser portion of that because of the isolation that is provided. Then tuned mass dampers, one example, I will start its explanation with the help of an example. Let me, or before that, sorry, before that, let me give you a better or a simple idea about this base isolation. In 2015, me and my group from Tokyo University, we participated in a building design competition in Taiwan, and this was a model which we prepared for that competition. The basic idea was to prepare a model or to demonstrate a better approach for seismic isolation or base isolation. This is a schematic diagram of the model. There were limits which were imposed by the organizers, that the covered area of the model should not be or should be within certain limits. Similarly, the height or the story height, the openings in the stories for windows as well as doors. So keeping all those conditions in mind, this was our final product with a central column, which is not shown here. And this is that model which is mounted on top of a shaking table. There are several, about 25 other teams were there from different parts of the world, and they were also competing. And these red colored objects are basically weights which are placed on top of this. About 5 to 6 kgs weight is placed on each floor level. And these limits are also imposed, which will ensure that if there is excessive deformation or lateral movement of the structure, then it will automatically be discarded or it will fail. And then this is the finally mounted structure. You can see some other structures also in the background. And this is final object or the structure which is ready for testing. Then in this video, you will see one example earthquake which is applied. And before this earthquake, about 4 earthquakes have already been applied on these structures. And there were several other structures which were placed here, which have already failed and they have been removed. This is 800 Gal. Gal is unit of acceleration or ground motion. 800 Gal earthquake will be applied in this video. And after that, a 950 earthquake will be applied and it will go up to 1200 Gal earthquake or 1.2 G earthquake. So this video will show you the performance of these different structures when they are subjected to a ground motion. There will be different components of the ground motion. First, there will be horizontal motion, then a bit of raking movement, a bit of upward component also. You can see that because of these base isolation provided to these structures, the superstructure is not moving like you will see for this structure at the later part of this video, or for this structure, that whole the top of the building will start swaying significantly. Some other approaches are also used, like the tuned mass damper also. So this one, it has already started failing. Maybe its base isolation system has stopped working. So this is what would have happened to these structures if they were not base isolated. So some of these structures will be failing in this ground motion, and the survivors, those will be going for the next round. So not on full scale, but this video should give you an idea that how the base isolation actually works. With the help of dampers, we can control the movement of the building, and we can significantly reduce the ground motion applied and the ground motion observed by the structure. So we were, our group at that time, that was the winner of this competition, one part of this competition basically. So then after having this idea, I hope you have got some idea that how the base isolation systems they work. Let's come back to the next topic, that is tuned mass dampers. So I will start with an example. Again from Taiwan. That is this building. So this is Taipei 101. Taipei is the capital of Taiwan, and 101 is because it is its floors. It has 101 floors, and you can see this picture I have specially attached to give you an idea that this is one of the most seismically active parts of the world, just like Tokyo or several other regions. But you can see that if proper attention is given to the design, to the civil engineering concept, such buildings there, they have been constructed there and they are performing really well. And these buildings, about 30-story building or 40-story buildings, they seem minor structures in front of this one. And in such high population density region, most of these structures, they have been specially designed for earthquakes, and that is why they are resisting very frequent attacks from earthquakes. This is another picture to give you an idea about the height of this building. And this was the tallest building in the world for a significant period of time. And this picture I had taken in 2017, and this gives you an idea that how these, which are skyscrapers from our country point of view, they seem quite minor in front of it. So now let's discuss that how they have managed to construct such a tall building in such a seismically active area. So one, apart from other devices or techniques which have been used, one major component or one major earthquake proofing technique that is used in this building, that is a tuned mass damper. So tuned mass damper is just like a pendulum which is suspended from top of this building, and it is suspended for the top 3 floors of the building. This is basically a significantly heavy mass, concentrated mass. These are steel plates which have been joined together in the form of a ball, and you can see in the next video that how they have been suspended from the top of the building. And the idea is simple, that whenever there will be excitation to this building by the earthquake, either in this direction or in this direction, this pendulum or this heavy mass, it will move because of its inertia, it will move in the opposite direction. So it will dampen out the applied ground motion at the top of the building, which will obviously shift from the bottom of the building, but it will significantly reduce the impact of the applied motion. So the designers, they claim that almost all the wind loading, because of its height, there is significant wind loading that acts on this building. So almost all the wind loading that is countered by this one, and a significant portion of earthquake loading that may act on the structure, that is also resisted by, or that is balanced by, this tuned mass damper. These are the dissipators which are provided. The idea is that it should not start swaying vigorously. There should be certain control on its movement. So they can be, or these are the actuators which can ultimately dampen out the movement of this ball. So I hope this would have given you an idea about the tuned mass damper. In simple words, it is the same concept as providing a water tank at top of a building. So when earthquake will act on that building from one side, the water will automatically slosh on the opposite side, overall balancing or up to certain extent dissipating the applied energy. But that is not a very controlled setup, because water, it will start moving without any control. But here, because of these controlled devices or actuators, its motion, it can be controlled. The idea is that overall the building should remain straight. So there are several other types of these tuned mass dampers. This is one of them, that's simply suspending a weight from top of the building. But there can be other types also which you can explore. Then the third type that we have seen here for a technique which is used by civil engineers, that we can improve the structural system. So we have three types of structural systems that we can provide. One is moment frame, the second one is brace frame, and the third one is shear wall. Shear wall is a structural component which is, these walls are basically shear walls, a very high reinforcement density steel or RCC wall. So the idea is that when the earthquake will try to excite or move this building in this direction, these two walls, they will come into action, and because of their higher moment of inertia in this direction, they will not let this building sway. And if the earthquake will try to move this building in this direction, these two walls, they will become effective, and they will resist the movement of this building. Then another option is that instead of providing a shear wall, we can provide bracings. It also acts in a similar manner, that if the earthquake will try to move this building in this direction, this link or this brace, it will try to move it. And if the earthquake will try to move the building in this direction, this link of the bracing, it will try to resist that movement. And similarly, for this direction movement, these components of the bracings, they will be activated, and they will try to reduce the sway of the building. And in this case, this is not that much preferred in seismically active areas. In most seismically active areas, shear walls are provided depending upon the nature of the structure or the budget available or the space limitations. Then the second preference is a braced frame, and the third one is moment resisting frame. In moment resisting frame, the whole lateral movement or the lateral action because of an earthquake is resisted by the beams and columns without a shear wall or without a bracing. So for any one location which is seismically active, the comparison you can see in terms of the cross-sectional dimensions, that if we will try to resist the whole seismic action only by a moment resisting frame, we will have to provide very thick cross-sectional elements. The beams and columns, their cross-sections will increase significantly. That is why this system is not that much preferred in case of high seismically active areas. And the cross-sectional members, you can see that the cross-sectional dimensions are significantly small because of the presence of these braces, because the lateral portion of the earthquake or the loading that is expected on this structure, that has been given to these braces. So overall beams and columns, their sizes can be reduced. The minimum sizes we get in case of a shear wall system, in which the minimum size of beams and columns we can provide and the maximum lateral resistance can be provided by these RCC walls. These RCC walls or these shear walls, in some cases they are automatically provided when we have to provide the lift well in a building. So the four sides of the lift well, they act as the four shear walls in most of the cases, not always, but if they are properly designed, then we can easily provide in a building four shear walls as the four walls of a lift well. So I hope that from this discussion you would have got an idea that being civil engineers, we can make sure that our structures they get sufficient or the desired capacity against earthquakes by changing or by selecting the suitable structural system. Uh, then just let me check that if anything is left for this lecture. Yes, so I will stop this lecture here, and in the next lecture we will discuss this part, the strengthening and retrofitting techniques in the next video, and plus the remaining three stages of disaster management cycle. Related to this one, whatever we have discussed so far, if you have any questions, you are very welcome to post them as comments under this video, or you can directly send me email. Thank you.